senior to me, was working on large-scale internet services for his dissertation, and then became faculty at Harvard, and did some really some of the most fun research I think any of us saw in sensor networks, deploying sensor networks on volcanoes, and everybody was very jealous of all of his efforts. Dealing with little wireless devices that are struck by smoking rocks from explosions. That was we think this node was lost to an explosion. So the kinds of extreme networks you don't really typically encounter. And so then Matt had a very successful career at Harvard, became a full professor, and then decided that he'd like to shift gears and be at Google. And so it's my pleasure, and without further ado, I'd like to introduce Matt Welsh.
Thanks, Phil. Great. Don't clap yet, you haven't seen the talk. Thanks, Phil. So, so I'll tell my own story about Phil. So I first met Phil when... So he was a first-year grad student at Berkeley, and when I first met Phil, I actually didn't meet him. I came into my office, and the monitor on my desk was gone. And so I emailed everybody in the group. I said, what the hell happened to my monitor? And I got this email back saying, yeah, this new guy, Phil, took it. So I hadn't even met him yet, and I'm already flaming him by email. It wasn't the last time he got flamed. All right, great. So what I'm going to talk about today is the work that my team does at Google on trying to make mobile web browsing super fast. So how many of you have a phone? Pretty much everybody. How many of you have like a smartphone, like something without physical buttons on it, right? Okay, and you use it to browse the web occasionally, I assume. Yes? And it's slow, and it's terrible, right? No, it's great? Okay, then my job is done. Thank you very much. It's incredibly slow, and not just, we're lucky. We live in places with really high throughput 4G networks and the latest devices and the fastest technology, but for the vast population of the world, the only way they ever get onto the internet is through a mobile phone. And their networks, trust me, are nowhere near as good as your networks. And their phones are nowhere near as good as your phones. And so this stuff matters a lot, and what we care the most about is making sure that the web browsing experience on mobile devices is as fast as possible. And ideally, you want it to be instantaneous. Ideally, you want it to be every time you hit a link, the web page pops up immediately. And currently, you hit a link and you wait and you wait and you wait 10 seconds or more for the web page to appear, and that's not what we'd like. So our job is to fix that. Let me just motivate some of what we're doing here. So I think you probably already know that the mobile web is huge, that currently we estimate around 2.5 billion internet users worldwide, and out of those, about 1 billion are mobile internet users. So about half, right, are mobile internet users. And this trend is continuing quite dramatically. I mentioned already that in many parts of the world, a mobile device is pretty much the only way to get onto the internet at all. Here's some statistics from on-device research. This shows in Egypt, 70% of the internet usage is from mobile devices only, right? India is 59%, South Africa 57%. Even here in the United States, 1/4 of the users of the internet only use mobile devices. This, to me, is really dramatic, because it just tells that there's this massive shift going on where the web started as, big, heavy Unix workstations on people's desks, and then it migrated to these things, and now more and more it's these things. And this is really where this is going to dominate. And I would expect in a few years to be seeing 10x the number of internet users primarily on mobile devices versus with laptops or desktops, right? And there's good data to support this. This is from Morgan Stanley. Now this graph is a few years old. I think it's from 2010. And the trend that they predicted was that mobile internet use would exceed desktop internet use in about 2014. So roughly 2 years from now, right? And so this is very exciting, and it means that we really need to get our act together because, frankly, the web on mobile devices is terrible. It's very, very slow. I'm going to talk about why it's slow. Any questions before I go there? No? All right, so let's first talk a little bit about how a web page loads. Okay, and I'm sure you guys have talked about this in the class, right? Yes? Okay, but let me review in case you weren't paying attention. So how do you load a web page? Well, what happens is you go to your phone, you type in the name of your favorite search engine or whatever website you want to visit. I won't make any recommendations. And the first thing you have to do is a DNS lookup, which takes the name to the IP address. And that DNS lookup is at least one round trip message from your device through the internet out to whatever DNS server might exist. Typically on a mobile network, that's going to be within your mobile ISP. So if I'm a Verizon customer, that server lives in Verizon. But I still have to go out over the internet, over the air, to get that. So there's one round trip just to get the DNS response. And then I have to establish a TCP connection. And I establish that by doing the Tcp Three-Way Handshake. I guess you guys have seen that too, right? So I have to send a SYN, and then I wait for an ACK, and then I send the SYN-ACK, okay? And that's another round trip, kind of 1.5 round trips, if you will, because I have to send the SYN-ACK at the end of the handshake, right? And then finally, I'm allowed to ask for the web page that I want. So I send a HTTP GET request saying, please give me the web page. And the server gets that, and it responds with the HTML for the page. And then the browser has to parse the HTML that it's getting. And notice all of the resources that are required to actually render the page. These are things like images, JavaScript files, CSS files, if there's like an embedded video, things like that. All of those things have to be fetched separately by the web browser over the internet in order to actually draw the page that's being requested. And so it makes a number of other requests, and those other requests in turn typically involve opening more TCP connections and more DNS lookups. Why would more DNS lookups be required at this point? Any idea? They might be hosted on different domains. So it's very commonly the case that if I load a web page, it might have an image, but the image is not on the same domain as the web page itself. It's on a different domain. Ads are a very common case of this, right? Advertisements typically are not hosted on the domain of the web page that you're viewing. They're viewed on other domains. So each of those other domains requires a DNS lookup and a TCP connection, and then the HTTP GET. You see where I'm going with this, right? So each of those steps is potentially quite slow over a cellular network. It's a little different than Wi-Fi or DSL or whatever blazing gigabit you guys have in the dorms or whatever these days. It's much slower if you're doing this over a cellular network, okay? And so what I'm trying to drill home is just the sheer amount of network traffic involved in loading a web page over a mobile network. Questions so far? Yes?
You're arguing that the cost is in the multiple requests as opposed to the actual amount of traffic, right?
It's both. I'm going to come to this in a moment. But what you're going to notice is that the highest cost here has to do with the round trip times over the cell network.
As opposed to the actual...
As opposed to the amount of bytes that you have to transfer. But I'll come to that in a minute. It's a good point. Other questions? Good? OK, so here is a way, and I'm sorry, you're not going to, don't try to read the text unless you sit in the front row and have magnifying glass. This is a diagram of a web page load. OK, don't bother about the text. And we call this a waterfall diagram because it kind of cascades down like a waterfall. This is the standard way that people in the web performance industry look at the timeline of the rendering of a web page. And what the chart shows is each row is a single resource required for this web page. It starts out with the HTML for the page and includes a bunch of images, a bunch of CSS files, a bunch of JavaScript files, various other things that it has to fetch, right? Each one of the rows has the domain it was loaded from. You can see most of this is for brown.edu's webpage. Most of these are coming from brown.edu. Those who have good eyes can see that these are coming from googleanalytics.com. Google Analytics being the site that a lot of websites use in order to track their usage. It includes some stuff on the web page. It calls back to Google Analytics. Google Analytics keeps a counter of how many times this web page was viewed. the size of the individual resource, and then the timing, and then I'll show you what the timing breakdown means. So each bar is colored according to the time for if a DNS lookup was required, how long that took. The yellow-greenish is the time it took to establish a TCP connection. The purple is the time that the browser sent the request until it started getting any bytes back from the server. So we'll call that the wait time. And then finally, the gray is how long it took to completely receive the response. So far, so good, right? So if you take a look at one of these, that gives you a sense of the breakdown. In this case, it took some chunk of time to do a DNS lookup, a little bit of time for the TCP connect, quite a long time until we got the first byte of the response, and then some other amount of time after we got the full response. Yes?
Why are some of the TCP connects so low?
Why are some? I'll come to this. TCP connections are really slow on mobile networks, but I'll come to that in a minute. Yeah? Yes?
So could you actually explain maybe why the DNS lookup would take so much longer than the TCP connections?
In this case, well, there's actually a bunch of reasons that that could happen. First of all, DNS sometimes is not done over TCP. It's done over UDP, which means it's lossy.
Okay.
Meaning that the packet, the initial query that the browser made could have been lost, and then it had to resend the query after some amount of time. I don't think that's going on here, because typically those timeouts are longer than what I see here. Random buffering and delays in the cell network, who knows? Right?
What could that have to do with if the DNS server has to make a recursive query? And
It's also, yeah, so it also depends very much on what the DNS server is doing. So this may not be actual like network delay. This may just be the DNS servers being slow or remote. For brown.edu, I wouldn't expect this to take very long, but
Are the cellular providers good at locating the DNS servers in good places?
okay, so one of the, so the question has to do with, are the cell providers good at locating the DNS servers in the right places? So typically the cell provider, my understanding is they almost all of them run their own DNS servers for their customers, and they'll typically put them close enough to the main metros that they serve users out of. That's been our understanding of what we can see. Now, this was run on one of the major US carriers, so I'd expect it to be pretty good in that regard. Other questions? Okay, so moving right along, let's take a look at this web page load. So here's one this is interesting. This is the brown.edu website loaded on my phone. And the first thing I want you to notice is it took 75 seconds to load this web page. Okay, that is an eternity. It's quite far from the less than 1 second load time that I'd like every web page on the internet to have. And then one thing you'll notice here is this one really long bar. And the size, which you probably can't see from where you're sitting, is 124 kilobytes. Took a long time to download, 22 seconds to download that one thing. What is that thing? That thing is an image. But the image is a background image that is completely covered up by everything else on the page. All that you can see is this. The full image is like 3,000 pixels by 3,000 pixels. So this is an example of a problem that we face, which is your browser downloaded the entire thing, right, for the sake of that little sliver. Right? So we would call this a not particularly well optimized mobile website. Right? Not to pick on Brown.
It still does it.
I only picked on Brown because Phil went there.
It still does it. I just checked.
It still does, yeah.
That's Fonts Hall. That's the student building.
So it was worth it. It was worth it. If I could only see it, it was worth it. Yes.
So is it accurate to measure the complete time that it took to download all the resources on the page if the user is able to start interacting before those are finished?
Okay, this is a very good question. So the question, I'll try to repeat the question for the video. So the question had to do with, do we really need to measure the time to load all the resources on the page when you don't necessarily need to wait for everything before you can interact with the page? This is an excellent question. It's actually a point of tremendous contention and debate within the web performance community right now. Okay, so here's the issue. Web browsers are not particularly good about telling you how long it takes to load a web page. This may come as a bit of a surprise. They generally report two numbers. One number they call the content load time, which is actually shown here in the blue. and the other is the onload time, which is the red, and that's the 75 seconds. The content load time is typically considered to be the time at which the browser has fully loaded the HTML and parsed it and figured out what it needs to do, but not necessarily loaded the images and the JavaScript and the CSS and things like that, right? Now, the onload time itself is a little tricky because the onload time fires at kind of an arbitrary point during the time that the web page is being downloaded and displayed. And that's because JavaScript that's on a web page can cause other things on the web page to be loaded. And so you don't necessarily know when you're done. In fact, you could easily make a web page that's never done by having a timer go off and load a new image every second, right? So what you really want to measure, in my opinion, is the time it takes to paint the first screen of the site. That is, anything that would be seen before having to scroll down. Yeah? But there's no good way of getting that information out of pretty much any web browser, desktop or mobile. Desktop browsers have some better tools for doing this. Mobile browsers are way behind on this regard. So for lack of a better metric, we talk about onload times, even though we know it's imperfect. Use onload time as a proxy for what the user will experience. But it's not perfect. OK, good. All right, so this is sort of intended to motivate the problem here. So why is the web slow on mobile? I'm going to go into a bunch of these things today. So the first thing is we have high round trip times on mobile networks. We'll get into the reasons for that in a moment. The web, HTTP and TCP, were not designed with 3G networks in mind. And 3G networks were certainly not designed with the web in mind. Right? The cell networks typically came out of just the desire to do voice calls. And data was, for a very long time, kind of considered a second-class citizen and not that interesting or useful. And they kind of shoehorned data transfer over the same mechanisms they were using for doing voice calls. And it wasn't a very good match. Okay? Recent evolutions in cell network technology have improved that situation. So data is now becoming more or less primary, and voice is kind of this thing that's off to the side because people don't do as much of it. Doesn't use as much network capacity. But we still have a long way to go. So there's this big mismatch between the two technologies. As you already know, most mobile devices are also much slower in terms of CPU and memory speed and so forth than a typical laptop or desktop computer. So this is another performance gap. I've already shown you an example of a badly designed web page that doesn't necessarily consider, for example, the screen size or which network it was meant to work over. And I already talked just a moment ago about the lack of good measurement tools. OK, so we have a lot of challenges ahead of us. Part of my job at Google is to try to fix all these things. The web, when I started on the web, now I got onto the web, back in, 1994-ish. And back then, web meant like this kind of thing, right? Like static HTML with blink tags, typically, right? And a background image was getting really fancy, right? And to many people, that is their kind of concept of the web. And I'm afraid to say that that's my generation, if you will, still thinks of the web that way, right? But the web is actually a full-on, complete application programming platform. If you look today at the set of things that we call HTML5, which includes, of course, the rich markup that you get from HTML and all of the styling stuff you can do with CSS. I actually saw a game implemented completely in CSS with no JavaScript support. It was like Frogger or something. I was blown away by this. It's like CSS is a complete programming language now. And of course, JavaScript. So JavaScript, you can do almost anything. You can get access to the camera. You can read the accelerometer. You can get the person's location. You can, play back audio and video. You can do all this amazing stuff. So you really have to think about JavaScript, HTML, and CSS as a complete application programming environment. So optimizing this is not just about taking this static stuff and making it draw fast, right? There's many more pieces to this story, okay? So here's what we're going to cover today. I'm going to go through a bunch of just issues to to kind of motivate the need for solving these problems and just tell you what the problems are. So we'll talk about what it takes to make a radio connection over a cell network. We'll talk about various things that browsers do in terms of opening parallel TCP connections. We'll talk about something called HTTP pipelining. Talk about caching behavior of browsers. We'll talk about carrier network proxies. This is when a carrier, a cell carrier, puts a box in their network that intercepts web requests from users and messes with them. We'll talk about JavaScript, and we'll talk about something called Speedy. Okay? So let's first talk about the mechanics of making a connection over a 3G network. This, to me, is one of the big performance challenges that we face. So if you go do a survey of mobile networks around the world, and you can get this data from lots of sources. We got this data from a company called Ookla that makes a little app called speedtest.net. Many of you have probably seen this. It's a little thing. It's got a big blue button. You hit speed test, and it shows these fancy dials of your latency and your throughput, right? Well, they have a lot of really good data on mobile network performance from users around the world. And you know, you can go break it down by country and carrier and network type and all that kind of fun stuff. But just to kind of give you an overview, if I take these various countries, and this is a table showing the RTT, the round trip time, that is the time it takes for a message to get from the phone to some server on the internet and back to the phone again. Okay? In South Korea, the average of all the users who ran speed test during the time window that I'm looking at here was 278 milliseconds. Let me put that into perspective. It takes 134 milliseconds for light to go around the Earth. Okay, so we're talking like 2x circumnavigations of the globe for one packet. And that's the fastest one. Okay? And you know, Vietnam 305, US 344. This is interesting. Vietnam is faster than the US. Well, that's because there's fewer users and fewer markets, and almost all of these are users in dense urban environments with fairly well-provisioned networks. It's also the case in places like Vietnam that they have cell networks that are underutilized. I'm sure you all have had the problem of trying to watch the cat video on YouTube from your phone and getting frustrated that it's not coming in quickly enough because everybody else in the coffee shop is doing the same thing, right? Vietnam doesn't yet have that problem. Right? There may be one person watching the cat video at a time. So, so there's a sampling bias here, right? And also, this is all of the US, including probably Hawaii and far-flung remote islands off of Alaska or something, right? But what's interesting is this diversity here, and it goes up. India, on average, which has a tremendously large and very diverse mobile network population, their average round trip time is 650 milliseconds, and in Nigeria it's pushing a second. Okay, this is really problematic, right? So if you ever think you're frustrated with how slow your phone is, go to Nigeria sometime and try it.
Speedtest.net on my phone, I got 56 millisecond ping time and 24 megabits.
Is that an LTE phone?
Yes, LTE.
Okay, so we're going to talk a little bit about LTE. So you got 56 milliseconds because you have a very shiny and probably burning a hole in your pocket hot, iPhone with LTE radio that's, you know, got a battery life of about half an hour. When it's on, right? If you left that radio on, your battery would be dead. It is amazing how much juice those things use.
Well, I never turn it on.
But it's also LTE, right? If you never turn it on, then you're fine. But LTE is the new 4G. It's not really 4G, but the marketing people have decided to call it 4G because they were tired of waiting for 4G. So they brought the bar down. It's sort of like you don't actually get to call yourself a third grader. You call yourself a fourth grader because you're tired of third grade. LTE can get round trip times in the sort of 60, 70 millisecond range and tens of megabits a second. Okay, so it's really fast, but it's hardly deployed anywhere yet. You're lucky because we're in Palo Alto, right? The throughput, the downlink throughput and the uplink throughput are typically very different on mobile networks. Downlink is the speed to get from the internet to the device, and uplink is the opposite direction, right? Average hovers around a megabit or two. This is not very good, right? Yes?
Isn't that asymmetry also prevalent in home networks, though?
You see this asymmetry to some extent in DSL, for example, in home networks. That's true. But you know, when we're on a mobile network, this is like modem speed here, right? So you already are dealing with something that was already slow. You've made it somehow slower by doing that. Okay. So just to give you a sense of what's going on here, and LTE, of course, solves a lot of these problems from a performance perspective, but it's just going to take a long time for the world to catch up to having that technology widely deployed. And it's not just about putting in the towers with new technology and getting the phones in everybody's hand and solving the power management issues. It's also about the backhaul networks that connect from the cell towers to, you know, the carrier network so that they're not congested, right? In a lot of parts of the world, they're actually using other wireless networks to get from the cell tower back to the core network anyway, so you have all these congestion issues. So what does the performance of the networks have to do with page load time? So we did a study looking at loading a bunch of web pages and then artificially tuning the speed of the network connection to see what would happen to the load time of the web pages. And this graph, it's hard to read the numbers. This is bandwidth in megabits, going from about 1 megabit up to 20 megabits. And you know, where we are today with 3G is around here, right? And this is the page load time in seconds. And as you see, you know, in the 3G range, the page load times don't get impacted too much as you push out in this direction. In other words, adding more bandwidth doesn't make web pages load faster. The thing that makes them load faster is reducing the round trip time. The round trip time is the largest determinant of the web page load time. It makes sense why, right? Because what I mentioned earlier was you have to do these DNS lookups and establish TCP connections and do HTTP gets for all these resources. So you're largely dominated by all of that round trip time overhead, not the speed of pushing the bits once you actually get them. Yes?
What proportion of that time is in the cell network, and what proportion is in the larger internet?
This is a great question. So the question has to do with what proportion is what's the breakdown of round trip time from the cell network to the rest of the internet? It depends entirely on what you're trying to do, right? If I'm sitting here trying to access a site like Google or Yahoo, which has great network coverage, then you know my latency to it could be less than 10 milliseconds or 20 milliseconds. But over a phone, it could be 300 milliseconds. So in those cases, the websites are fast and they're well deployed geographically. The most of it's going to be in the cell network. But if I'm trying to access, you know, if I try to access some website for a hostel in Laos from my phone right now, then the packets still have to traverse all these long links on the internet that are not as fast. So there I'd expect more like a 50-50 breakdown. Yes?
Browsers throttling how many connections they'll open at once.
I'll come to this. The question has to do with how many connections does a mobile browser open at once, and the answer, the preview of the answer is way too many. And I'll show you that in a moment. That's a good point, though. Okay. So one of the biggest problems we face is when you want to just talk to the cell network, the phone has to first negotiate with the cell network to get a radio channel. Okay? And it turns out that process can take several seconds. In other words, to send one packet, before I can even send the packet, there's a multi-second negotiation with the cell tower to get the resources allocated so that I can start transferring data. And if you're thinking, gosh, that sounds terrible, this is a huge problem, isn't anybody doing anything about this? The answer is you'd be right. Yes, this is a huge problem, and lots of people are worried about this. So to give an example, every time I want to, if I receive an email notification on my phone, just one email notification eats up something like 4 minutes of my battery life on LTE. 4 minutes of standby time. It's like, wow, how did that happen? It's because the packet wants to come down from the internet to the phone, and the phone has to ramp up and get a radio connection, and then it talks to the radio tower, it gets the one packet, but then because the phone doesn't know what's going to happen next, it leaves the radio on for like a long period of time after that, thinking it might do more communication. But nothing happens. But the radio's on, and this is killing your battery.
What about the
the connection establishment process makes it take several seconds, because it seems like a lot of things happen in several seconds.
Okay, yeah, so why does it take several seconds? The answer is it's actually very complicated. So if you go into the specs, there's this big stack of documents called the 3GPP specifications, which describe at a low level how cell networks work. And you can go download these for free on the internet, and there are many, many thousands of pages. And you can go find the section that talks about how the phone communicates with the cell network to establish a radio channel. And they have a diagram of all the messages that are sent. The diagram covers 3 pages. Okay? And it has to do with all this registration and overhead and negotiation and sampling the channel and figuring out how much bandwidth I'm going to give you, and are you actually allowed to be on this network, and there's just a lot of issues, and a lot of it is complicated by the fact that we expect handover between cell towers to work seamlessly. If I were walking down the street and either on a call or browsing the web, I don't expect it to just drop the connection if I get bounced from one cell tower to another. So why can it possibly take several seconds? Just because there's a lot of overhead in the underlying protocols. And this is another example where the protocols were designed to support phone calls. Right? Where, well, it's okay if it's going to take a second or two for me to kind of dial the number and get the phone call going. But here I am wanting to browse a web page, and that may not be a good idea. Okay? So try this sometime. You build a little web page, and you have a piece of JavaScript on the page that loads a little tiny image, like 1 kilobyte image, but then increase the amount of time between the loads. Okay, so you start out loading it 1 second interval, then 2 seconds, then 3 seconds, and watch what happens. This is what it looks like on Wi-Fi, and what you see here is the increasing intervals, but each one it's labeled says about 100 milliseconds, 120 milliseconds. So it's taking the same amount of time regardless of the spacing. Okay? You do this on a cell network, and here's what you see. With 1 second delay, 2 second delay, and then when you go to 3 second delay, suddenly these things start taking multiple seconds to load. And what's going on here? What's going on here is the cell tower has a timer. And when I'm trying to load something, if I have an active radio connection and I wait for longer than this timer, the cell network says, well, you must be done using the radio. I'm going to shut down your channel. Right? So the next time you wake up and say, I would like to load the image, you kick back into that multiple second negotiation process. You follow me? And have to do that whole thing all over again just to load the image. Right? So the timing at which these things happens matters a lot. So it shouldn't be surprising if I'm sitting here reading, the New York Times, and I've spent a few seconds on an article, and I'd like to click to the next one. I click it, and it seems like it's taking an awful long time to go to the next link, and it's because it's renegotiating with the network to get a new channel. Yes?
How much of the round trip time is determined by the radio connection establishment versus just the latency between the towers?
How much of the round trip time is so the round trip time numbers I gave you all assumed an active radio channel. So if I've got an active radio channel, it's still taking 200 milliseconds or 300 milliseconds. This is an additional overhead on top of that just to get talking on the radio in the first place. So here's this is called what the industry calls the radio resource control state machine. And the concept is your device is in one of 3 states. There's actually many more than 3 states, but for the purpose of this, I'm just going to simplify and talk about 3 states. Okay, so there's 3 states. I'm idle, meaning I'm not talking on the radio at all. If I start to transmit, I have to get promoted to a special state called the DCH state, which stands for dedicated channel. And the DCH state means that I've got an active radio connection and I can send and receive data. But that process, as I mentioned, can take a couple of seconds to do that promotion. Okay? And then in this particular network, it depends on which network you're on. Actually, every network in the world is different. So T-Mobile is different than Verizon, is different than AT&T. But there'll be a several second timeout. And if I'm idle for that period, what I do is I drop down to something called the Fatch State. The Fatch State stands for Forward Access Channel. And if you asked me why it's called that, I would not be able to tell you. I knew at one point, but I don't now. Think of this as this is a dedicated radio channel. This is a shared radio channel. That means multiple devices on the network can use it at the same time. You don't get as much throughput. It's higher latency, but it saves the network from having to allocate a dedicated channel to each and every phone. So it's sort of lumping you all together into one shared channel, which is not as good performance, but if the expectation is you're not doing very much on the network, that's fine. And if you start to send or receive more than a certain amount of data, you bump back up to getting a dedicated channel again. But while you're here, think of this like purgatory. You don't do very much. You drop back down to an idle state, and you're off the network entirely. Yes?
So if I'm understanding this diagram correctly, it would actually be better if your phone would just like at random intervals like keep that connection alive, and it would like be bad for the network but good for you, I guess.
Okay, so this is a great suggestion. The suggestion is, why doesn't your phone just constantly ping the network to keep the radio channel going, right? Mm-hmm. It's a very good idea. From a performance perspective, it absolutely works, right? If you wanted really fast networks connections on your phone, run a little program on the phone that does every second ping something. Yeah. Verizon will hate you for it, and they'll put a little poster with your face on it in their office or something. So this causes, there's two big problems with that. The first problem is the capacity problem, is that the cell networks are not prepared for everybody's phone being on the network all at the same time, right? And the second problem is it'll completely kill your battery, because the amount of power that you use is thousands of times higher in this state than in this state. And so we've explored doing some of these things, and you could add little stuff to web pages to kind of keep the radio alive, and then when you navigate to the next page, it's faster, but it just totally eats battery life. It's terrible. Okay. Browser connection limits. This came up earlier, so I'll get into it. So web browsers typically open multiple connections to download content in parallel. And that's just to speed things up. And this practice derived from the days of, the early days of the desktop web, when people started to notice that if I were actually downloading multiple images at one time, I got the web page rendered faster than if I downloaded them one at a time. It makes perfect sense. Now, if you go back to older versions of Android, what you'll see is that the browser only opens 4 connections simultaneously. And it's kind of hard to work out how that's happening, but the way of doing it, this is a load of the brown web page, and you will notice only 4 of these green bars, meaning TCP connections, got opened. And if you kind of look, you can sort of see how they group into 4 parallel connections. It's not immediately evident from the picture, but you can kind of work it out. Plus, I know the guys on the Android team, so I could just ask them, but right. Okay, so that was the old version of Android. New version of Android, more recent version, Ice Cream Sandwich, actually completely changed this, and they open 6 connections per domain, but allow, I think, something like 50 parallel connections, so that you can have many domains with lots of connections. So they changed this to be more like what desktop browsers do. Okay? And so this is changing the landscape of what it's taking to load a web page, because now we can take advantage of lots of parallel TCP connections. Right?
Not a particular question.
Oh, I'm sorry. Yes?
Do mobile browsers do that just when they're on like LTE or 3G networks, or do they do it on Wi-Fi as well?
Yeah, the question is, do browsers do the same thing on Wi-Fi versus 3G networks? I'm actually not aware of any browser that has different behavior in this regard when it's on Wi-Fi versus 3G. They all seem to behave the same regardless of what network they're on. Yes?
Is it necessarily a good idea to go and open dozens of connections if you're on like a slow-edge network?
I want to come to this in a moment. But yeah, the question is, should I be doing this given how much time it takes to open all these parallel TCP connections? Right? So I'll try to answer that in a minute. let me finish the rundown. And then if I do this on iOS 5, it's actually kind of harder to get good numbers. The reason you don't see the greens on here is because the way you instrument iOS doesn't give you that information, and so we don't actually see the TCP connections being opened, but you can infer things. But if you stare at this, it sort of looks like there's a lot of parallel TCP connections going on, right? And Chrome on Android behaves the same as Ice Cream Sandwich's browser. 6 connections per domain and 50-ish total maximum connections. Why? Because the Ice Cream Sandwich browser on Android used the same network stack as Chrome. So it wasn't Chrome yet, but they took the bottom half of Chrome and ported it over. So it behaves the same. So here's the summary. Depending on your browser, you're going to get very different behavior in this regard. And it takes a lot of experimentation and probing to even find out what the limits were. I actually asked the guy on the Android browser team what the limits were, and it was a very long, protracted conversation about the different cases and what it would do. So this is a crude approximation. So the question was raised, are more connections always better? Well, why do we have parallel TCP connections? The reason is we'd like to use as much bits over the network as we can, right? We'd like to do that. But on 3G, this isn't always a good idea. You have to pay the cost of the handshake for every connection, which can actually make things slower if in some sense you weren't going to amortize that overhead by doing lots of stuff with those connections, right? So if I open up 30 TCP connections and on each one downloaded one thing, that probably didn't make a lot of sense, right? And the other problem is having all these connections open means that they're all contending for the radio channel at the same time, right? So if I had 30 TCP connections all trying to download a megabyte file, this is not going to perform as well as having a smaller number of connections. So there's some magic number in between 4 and 50 that you would like to use. And this is an active area of research. Yeah?
Can you talk a little bit? So you're saying that, like, if I were to open 30 TCP connections, not that it's going to take 6 seconds to do so. It's not like these 200 milliseconds.
No, those would be over. Yeah, right.
Yeah. So is it like, what would the time increase be to do these 30? They're not going to take 6,000 milliseconds, but they're not going to take just 200.
Right. It's very hard to know. I mean, you'd have to kind of dig into these numbers here and look carefully at all of the interactions and what's going on. And what happened here's part of the challenge, which is anytime there is congestion in the network and packets get lost, things really go to hell. And the risk is if I had a situation where the user was in the middle of doing a handoff or there was some congestion in the network and all of these connections effectively lost their ACK, then they'd have this very long timeout period before they tried it again. So in some sense, it's like you're lining up all these things, and one bad condition over the radio can just hurt them all simultaneously. Right? Yeah.
Do data connections have smooth handovers then, like voice on?
Typically, yes. I mean, it depends very much. Handovers within the same cell network, within towers within the same kind of region of the cell carrier network, typically will hand over seamlessly and you won't have a problem. The challenges come when you go between different regions or different carriers and things like that. But there's lots of variation here. The industry is not uniform in this regard. Okay, so let's talk about HTTP pipelining. So this was a proposal that was actually included a long time ago in the HTTP standard. You guys have studied HTTP? Little bit? All right, so here's the concept. In HTTP, I say get foo, and it returns foo, right? Have I lost anyone? Okay. Right.
They know that much.
All right. So HTTP pipelining says get foo, get bar, get baz. I do 3 gets, and then the server returns foo, bar, baz in that order. It's very important that it's that order because you have to match the reply to the request. So the idea here was I can ask for multiple things on one connection and get them back kind of pipelined or streamed back to me without doing them one at a time. So I can ask for multiple things at a time. Good? Now this was actually introduced in the HTTP 1.1 standard, but almost no desktop web browsers turned it on because at the time it was thought this was going to break the internet. Because all of these proxies and middle boxes in the internet that intercept your traffic and try to rewrite things, and like, a lot of these old Wi-Fi access points try to do funky things when you browse the web, right? And it was thought that this pipelining was not going to be compatible with all those middle boxes and proxies in the internet, and so browser vendors were very hesitant to turn this on. They thought it would cause problems. Well, the Android browser turned it on one day, and no one noticed any problems. And a few 100 million devices were using HTTP pipelining, and it seemed to work okay. And so I think we've all agreed now that it works okay, but it was one of these interesting cases where no one noticed that Android had done this. So what happens in Android Gingerbread is you'll see this multiple requests with the same start time, but they have staggered completion time, so you can kind of work out that it's doing pipelining. Mobile Safari turned it on in iOS 5. Android Ice Cream Sandwich and Android Chrome turned off pipelining. And again, it kind of comes down to this. This is a little bit of black art. No one really knows if HTTP pipelining helps or hurts mobile performance. Seems like something we should probably answer. But there's been lots of studies, and they have conflicting answers. And so people are like, meh, I don't know what to do. Let's talk about these middle boxes, these proxies that live in the internet. So if you have this idea, and Nick has probably drilled into something called the end-to-end principle, right? It's complete garbage because it doesn't actually exist. Right?
So John came 2 weeks ago and talked a lot about all the middle boxes.
Good, good. So you've heard about middle boxes. Okay. So we all believe in the end-to-end principle, and Phil probably has a tattoo of it somewhere. But it's not. The real internet is more complex than that, right? So we had this thing. We're looking at this page at Google, and we noticed something really weird. I made a web page, and it just had a big JavaScript file, and I wanted to just measure the time it was taking to download, and it was like a megabyte of JavaScript. And I made the JavaScript. I was very clever. I wanted a megabyte of JavaScript, so what did I do? I just held down the X key until I got a megabyte. So it's like it's a string containing a million X's, basically. There's no content. So I loaded this, and yeah, it works fine on Wi-Fi. And then I loaded it on our phone, and we noticed the size had magically shrunk to 7.6 kilobytes. I'm going, what? 7.6 kilobytes. And then I noticed T-Mobile has a proxy in their network that's turning on Gzip for everything, right? So most web browsers know how to speak Gzip compression. So when you download something, you don't get the raw text. You get Gzip stuff, and then the browser uncompresses it. This is good. But T-Mobile was doing this magically for us. So, boy, was that confusing for about 20 minutes. We had no idea what was going on. And then we said, hey, and then we noticed some carriers do this and some don't. So this is another thing that's not uniform. Right? That if I'm browsing the web on T-Mobile, I'm going to get a different experience than if I'm browsing on Verizon for the same web pages. Yeah.
Is it? I heard this a couple years ago. This may not still be true. Is it still true that there's proxies in like mobile networks in like Africa that actually break Gzip?
All right. So the question is, are there proxies in mobile carriers that break Gzip?
Basically, the reverse of.
Why would they do that?
Because they're broken. I don't know.
So all right. So I could imagine a situation where I am not sure if my phones that I'm trying to support can do Gzip, so I un-Gzip things so that I can deliver it to the phones and knowing it's not going to break. I don't know if that's the case anymore. It's a great question. There's lots of weird stuff on the internet, and you don't fully know what's out there. There are proxies, for example, that take YouTube videos and recompress them so that the quality of the video that you see is not the quality that YouTube is serving. It's a recompressed version. It adds Gangnam Style to every video. It's amazing technology.
That is pushing it too far to the upside down internet for me personally.
Right. Okay, so another big problem on mobile is that the browsers and the CPUs are just slower. And I mentioned earlier how web pages are extremely complex. There's lots of JavaScript involved. I'll give an example. There's websites that we've seen that download 150 kilobytes of JavaScript for that little drop-down menu you get. When you tap the link, then the navigation, it does the animation. It glows, and there's like a shadow and stuff. 150 kilobytes of JavaScript for that, right? It's very, very clever web design, but not really the right thing for mobile, yeah? So you benchmark JavaScript performance on different platforms. One of the standard benchmarks people use is something called SunSpider. SunSpider measures a whole bunch of different things, and then it reports a number, and the number has a sort of a time associated with it, and lower is better. So you run it on, like, you know, a MacBook Pro or something, it's 266. Who knows what the number 266? Don't worry about what 266 means. That's just the number of the benchmark. I do this on a Galaxy Nexus phone with the Android browser. I get 1900. I get 1500 or so out of Chrome. This is, you know, nearly 10x what my laptop was doing, 10 times slower. And then I do an older iPhone. I mean, this really tells you a lot about what's happening. I mean, you say, well, the phones kind of all look the same from the outside, but you think about what's inside, and you say, wow, those iPhone 3GS is so much slower than a modern phone. The iPhone 4S is pretty fast. The iPad 2 is pretty fast. But they're still 10 times slower than a laptop. Okay? So this means that all this stuff that you're doing on websites for mobile has to take this into account. You guys know about browser caches? No? Okay. So here's what a browser cache is. A browser cache is when you're loading web pages, I don't want to reload something that I've already got. So I keep a copy of it in the browser. And if it's still relevant and it's not stale and it's the correct content, I can serve it immediately out of cache as opposed to fetching it over the internet. Okay? So mobile browsers have really small caches. The old Android browser had an 8 megabyte cache. iOS 5 seems to have a 100 megabyte cache, but every time you restart the browser, it disappears. Chrome has 250 megabytes. But, you know, typically we're seeing 512 megs or a gig or more on laptops and desktops. So what this means is the amount of stuff that I can keep locally on my phone and not have to fetch it over the network is much smaller on mobile devices. Right? So increasing this is great. And it's interesting, you know, these phones have 32 gigs, 64 gigs of flash memory in some cases. I mean, you could really use the storage capacity if you haven't filled it with, you know, Angry Birds and whatever. You could use this capacity to save a lot of network traffic, right? The other thing that we run into, I'm not going to go into this in a lot of detail, is a browser's one thing. But many, many native apps for mobile phones also basically embed a little browser inside. Right? For the longest time, the Facebook app for iOS wasn't really an iOS app. It was a skin around a web page. Right? And I believe on Android, that's still what they're doing. And in many ways, this is great because it makes it easier for them to upgrade. They can change features just by changing the content of the web pages on their servers. They don't need to change the app. However, if you go through the native APIs or the native libraries for using the web from a native app, you're not getting the same performance and the same behavior that you get through a browser. Right? There's a classic case where Apple, for some reason, I don't know the reason for this, in their browser, if you loaded a web page in mobile Safari in the browser on an iPhone, it would use their really accelerated JavaScript engine that was so much faster. But if you loaded the same web page in a native app, they turned off the acceleration. I don't know why, but it meant that you weren't getting the same performance.
Apple says it's because of security, that they think that they sort of have audited the Safari code and think that errors in Safari will not lead to sort of JavaScript exploits due to breaking the JIT and running native code, and that that the old interpreted JavaScript is considered safer for third-party apps.
That sounds plausible, actually. Yeah. So this is
It's
Apple's saying this might be because of a security concern.
Developers still complain, but that's Apple's official, I think, explanation again.
Okay. So the point of this is if you use the standard libraries in Android for accessing web pages, you get no caching at all. So this creates a whole bunch of issues. Okay, so I think this is my last slide. Oh, no, it's not my last slide. I've got one more slide after this. So just to sum up some of the issues. So we have high round trip times. The connections can take multiple seconds to get established. Pipelining, not clear if it's helpful or not. The carrier network proxies will confound whatever efforts you have to understand what's going on. JavaScript isn't always very fast, and the caches are not really created equal. So I want to just touch a little bit on Speedy. How many people have heard of Speedy? Did you guys talk about it in here? All right, we'll talk about Speedy for a minute. Speedy's a lot of fun. We've done work on it. So Speedy is a replacement for HTTP, and it's an open standard. It was developed by Google, but it's an open standard. It's built into Chrome, Firefox, the Kindle Fire. I think actually Opera has it as well now. And effectively what it does is, if you think about HTTP is a very old protocol at this point. 20 years old? More than 20 years old? Right? And HTTP has gotten us a long way, but it's not designed for modern web pages. It's not designed for modern networks. Speedy sort of rethinks a lot of this and restructures the way that you fetch content over the internet and streamlines a lot of the performance problems. So I'll give an example. In HTTP, the requests and the responses are all plain ASCII, right? Get space index.html carriage return new line in ASCII, right? And this was great. I mean, network engineers love ASCII because you can just read it and I can type it, right? But it's not very efficient from a network perspective. Speedy does everything with a binary encoding, and it uses heavy amount of compression and all that kind of stuff, right? So it's meant for machines to talk it, not humans to talk it, which seems about right because the number of humans that speak HTTP is vanishingly small. So the other thing that Speedy does is instead of opening up all these different TCP connections, it uses one connection and multiplexes it. So I can ask for things on a single TCP connection and get them out of order. So remember I said this about HTTP pipelining earlier, right? You ask for multiple things, but you have to get them back in the same order. Speedy allows you to get the responses out of order. So for example, if I ask for 5 things, the web server might already have 2 of them ready to go, but they're not the first 2 you asked for, right? It goes ahead and sends you the first 2, and then can take its sweet time processing the other 3 requests. It does header compression. So if you've ever played around with HTTP, one of the things you're going to notice right off the bat is every request you make to a web server has this big chunk of like a kilobyte of headers. And the headers have all this information in them, like what kind of browser am I running? And do I accept Gzip? And what are my cookies? And all this information goes with every single request. And it's totally idiotic, right? Because it's not like I've upgraded my browser in between multiple requests on the same web page. But yet every single request carries the same string of information, right? It's very, very expensive. Speedy solves this just by using compression on the header so that that redundant information is eliminated. And so I'm effectively sending it once instead of many times. This has great, great impact. Another really cool thing that Speedy does is it actually allows the web server to send stuff to the browser that the browser has not yet asked for. So think of it this way. I connect to CNN.com. So currently, how does it work? I go to CNN.com. I ask for CNN.com. It sends me back an HTML page. And the browser spends some time, and it looks at it and goes, oh, I need to download these 50 things to get CNN.com, right? And so the browser has to ask for each one of those things in turn. But with push, what can happen is you say, I like CNN.com, and the browser, the server can say, aha, well, I know you're going to need this and this and this and this. Let me just send you that stuff now because I know you're going to ask me for it. So I'm going to save you the trouble. Boom, push. It'd be great for performance. Phil.
Here between the client-side caching in the sense of the most common things like, oh, you want the CNN logo, but I already have it. And so it seems like the server can safely push really dynamic content. Right?
You can only really push things that you know the client doesn't have cached. But there's so much stuff out there that websites, for one reason or another, decide not to make cacheable.
Ads.
Ads is a great example. So I can go ahead and push the ads to you without you having to wait to ask them. Okay, so Speedy is the basis for what's going to be called HTTP 2.0, which is the next revision of the HTTP standard that's currently being developed by the W3C.
On laptop and desktop browsers, they will often prefetch. They'll start looking up DNS entries and
that's right.
Going and downloading next HTML off some of the links it finds on a page. Presumably a phone doesn't do that because of the radio resource?
No, actually phones do that. So the question is, so modern web browsers are really good about trying to prefetch things that it needs for the web page. So it's not exactly, there's two kinds of prefetching. There's kind of, as the HTML is coming in, before all the HTML is landed, the browser starts noticing things that it should fetch. So it goes ahead and kicks off those things. But there's also, Chrome, for example, has some features that actually allow it to preemptively fetch things for future page loads. Okay, so Google search result pages have this funny feature where the first link in a Google search result page is sent to your browser while you're watching. So if I type CNN in Google, you'll see all the list of links. Which one are you going to hit? Probably the first one, yeah, because you're looking for CNN. What happens is Google sends the content of CNN to your browser while you're sitting there looking at the search results. So when you click on that first link, CNN is already there. You didn't have to wait for it. So that's a feature of Chrome. That just works the same way as Chrome on Android. So Chrome on Android does exactly the same thing. Right? Okay. So Speedy is potentially great for mobile. So here's a study we did. This is a Wikipedia article, and this time I decided to pick on Harvard. So this is the Harvard Wikipedia article loaded using regular old HTTP. And you'll see there's like a bunch of stuff on this page. Most of them are images. Never mind these 404 not found. This is just because I took a copy of the web page and replayed it later. So this is just an artifact. But you'll see all of these brown segments are the browser waiting to get one of those few TCP connections available for it to make a request, right? So what's happening is it's able to ask for the first 6 things, but after that it has to wait in line for one of the available 6 TCP connections in order to make another request. So it can't even ask for more until it's done getting some more stuff, right? So with Speedy, boom, everything gets asked for at the same time. It issues all of the requests basically at the same time. And then the requests come in at just different times. Right? So effectively, you're making all your requests at once, and then the stuff is streaming back to the client from the server. It's a much more efficient use of the network. Basically packs everything in. Yeah? So we did a little study. There's a blog post you can go look up if you want to see the details, where we studied, I think, 77 popular websites. We loaded them with HTTP, and then we loaded them with Speedy. We measured the time. This is on mobile. And we found that the red is Speedy and the blue is HTTP, and the x-axis is the website. And we found that, on average, Speedy reduced the performance, or reduced the load time by 23%. And there's one site, you're going to notice one site that actually did worse on Speedy. I left that one in there so you'd believe the numbers. It was Huffington Post. I haven't actually looked at why it didn't do as well on Speedy. It's a good question, but it consistently was slower on Speedy for some reason. Don't know why. Questions? Yeah?
Previous slide, why were there multiple, it looked like sometimes there were multiple resources being sent back at once. How is that? In what manner was that actually happening with?
There shouldn't be.
Gray is
Oh, I'm sorry. This is really an artifact of how this diagram is drawn. There's one TCP connection here, and the trick is Speedy operates over SSL, the secure sockets layer. And so we don't get to see the individual packets because it's secured. It's encrypted. So the way that the tool draws it is just as the times that it believes that they've started and finished. But there's really one connection here, and so, but yeah, they are overlapped because the way Speedy works is that it sends things basically out of order and it chunks them. It chunks them. I failed to mention this. So it doesn't send one full resource at a time. It actually breaks it into pieces. Yeah. Yes.
So you said Speedy uses SSL.
Yes.
So how does was that a comparison of Speedy versus HTTP or versus HTTPS?
This is versus HTTP.
So
this is including the SSL
yeah, so
overhead.
that's interesting. So 23% doesn't seem great, but perhaps it'd be interesting to see how it compares to an HTTPS connection, which would be encrypted as well.
Well, actually, HTTPS is typically slower just because of the overheads of establishing the connection. But that's amortized here. The question, 23% doesn't sound great. From where I sit, this is awesome. Let me tell you, there is not one optimization technique that people have proposed to fix mobile network performance that got anywhere near 23%. So this is additive with other things that you do, but 23% just for making that one change is pretty substantial. Yes?
Sorry, I might have missed this, but is this evaluated on mobile or on desktop?
This is mobile. Yeah.
Did you also do the same test on desktop?
Oh, there's all this. Yes, I mean, there's all these other blog posts and papers and things about Speedy performance on desktop, and it does perform better. Yes.
So what does the deployment look like of Speedy on the server side? Because I mean, if these 77 websites obviously support it.
The way that we set this up is I just basically set up a proxy to pretend that to take. What I did was I took a copy of these websites and I served them out of my own server that knew how to speak Speedy. So this is if all these sites started serving Speedy, as opposed to HTTP.
So you included server push, for example.
There's no server push in these experiments. I have other data that talks about that. Hint, I don't have this published, but it's like 34% improvement over Speedy if you add push.
Wow.
It's really good. Yeah, push is great. Yes?
Out of curiosity, when you issue an Ajax query, or multiple queries, if I issued multiple queries, would I open a separate connection for each one or no?
With Speedy?
No, just in a browser.
With a browser. Okay, so browsers, Ajax is when you have JavaScript on the page that makes a request to ask for some things. It depends entirely on the browser, whether it uses an existing pool of connections or opens a new one. Most browsers that I'm aware of, they basically just maintain a socket pool that they have associated with a domain. So if you're making an Ajax request to a domain that you've already got an open socket on, it will reuse one of those sockets. But otherwise, if it doesn't have a socket open, it will have to open one.
Because it seems as though you could write a JavaScript Speedy-like something that would work over HTTP that just issued a bunch of Ajax requests and then loaded.
Okay, this is a great idea. Okay, so the proposal on the table is simulate Speedy with JavaScript over HTTP. And actually, there's some websites that do all kinds of stuff like this. They break the site into a template that is loaded first and stored in the local storage API within your browser, and then the other stuff comes in and JavaScript interprets it and pulls the stuff out of the local storage and renders. There's this one crazy optimization I saw last year at a conference. This guy was talking about the time to parse JavaScript for the browser to read the JavaScript and interpret it and figure out, not to run it, but just to figure out what it is, can sometimes be quite slow. So their technique was as follows. Take a bunch of JavaScript, comment it out. Okay? Follow me. It's commented out. Then another so it gets loaded. Then another piece of JavaScript at the bottom of the page, after everything else is loaded, manipulates the DOM to remove the comment tags, which forces the browser to suddenly notice there's JavaScript there and parse it and execute it. So it's like you're stashing this little thing away, but it's bundled up in a way that the browser won't look at it until you do this other piece of magic to arm it. The web performance community is full of things like this. And part of our challenge is we're trying to make all mobile websites faster. And there's a bunch of best practices and things in a lot of education. There's books and things that web designers and web developers are supposed to follow these practices to get the best performance. And part of our goal is to try to automate as much of this as possible so that web designers don't have to put as much effort into it. I want to say that's it. Thank you very much. And I think we're just about out of time, so I'm happy to take a couple more questions. Questions? Yes.
I'm really curious what you think of things like Amazon Silk Browser or Snap2, which basically package things in the cloud for delivery to mobile in a better format.
Yeah, the most popular version of this is Opera Mini. So Opera Mini is a browser that runs on both smartphones and feature phones. And basically, all the website rendering is done on their server, and it ships to the phone. I mean, it's not exactly this, but think of it like a picture of what the website looks like. Not exactly, but that's sort of an idea. And Amazon Silk doesn't go anywhere near that far, but that's what they've talked about potentially doing in the future. These are interesting technologies. They run a very serious risk that they fail to keep up with the emerging web standards. And so Opera Mini in particular has this big problem that it can't run most JavaScript out there. And so it lags behind. It works well for the web as it looked in like 1999. But it is now 2012, and people are trying to do increasingly sophisticated things through web pages that Mini just can't support. And so there's this constant tension here where, you know, conceivably all of the browser could live in the cloud, and then the only thing that you have here is a screen. But how about interaction? What happens when I touch on something and that has to trigger something that's going to execute? That's going to be too slow if you have to send all of your touch events to the cloud in order to run them. So there has to be a partitioning between what runs on the phone and what is done in the cloud. So a lot of what we're doing at Google is we have a system called PageSpeed. And PageSpeed takes websites and it optimizes them before sending them to the browser so that they're much faster. It solves a lot of common performance problems. It doesn't go anywhere near as far as things like Opera Mini, but it's standards compliant, and it allows web developers to take advantage of all those APIs. So I think it just depends on kind of where you stand. But my belief is that HTML5 is here to stay and that we should support it. Do I have time for one more?
Yeah, we're just going to do the attendance code.
I don't know what that means, but okay.
Yes. I'm curious as how you handle compatibility of Speedy with older versions, say 1.1 of HTTP. When you make that initial request from the browser, you're uncertain of whether or not the remote end supports Speedy.
Okay, so the question is, how does a browser know that the remote end supports Speedy for backwards compatibility reasons? I really don't know what this is. This is cool. It's like a top secret thing. Okay. So the way it works is you open up an SSL connection, and then in the initial handshake with the remote site, you mention, by the way, I can support Speedy. The browser says that. And the server goes, oh, OK, cool. And then we negotiate Speedy. So there is an initial negotiation step. And the way that's done is backwards compatible. So a non-Speedy browser won't notice it and will just use HTTPS.
Is that communicated through an HTTP header?
I think it's actually done. There's a couple of different mechanisms. And I don't want to go on camera saying exactly how that negotiation works.
Okay.
Yeah. But yeah, it's something like that.
Yeah, so what made me think that Matt would be a great speaker is that I was at a workshop which he helped organize at Google last summer, and he said, which I think was true, that the mobile web today is kind of like the web that we encountered like in the 90s when it was actually really terrible. And then a lot of the 2000s were spent doing a lot of intelligent things to make the web as good as it is today. But unfortunately, the mobile web is where we were in 1999. And so you see things like HTTP 2.0 and Speedy, just in the same way HTTP 1.1 added Keep Alive, right? These techniques to actually make the application platform adapt, which is why I think there's a particularly exciting area of what's going on in networks today. So let's thank Matt again.
Thank you very much.